Hello, today I've got an interesting USB charger that uses zero standby power. So let's tear it down and take a closer look. This is a 67-watt USB charger from Belkin's Boost Charge Pro series. It looks like a typical USB charger, but according to the packaging, it uses zero standby power to save energy. With electricity rates rising in recent times, many people may find the zero standby power feature very appealing. So in this video, I'm going to check how much the standby power is reduced compared to other chargers, and whether there are any advantages or disadvantages to reducing standby power. I'll also be taking this charger apart to examine its internal structure in more detail. But first, a quick shout out to today's sponsor. If you're looking for low-cost PCBs, I highly recommend JLC PCB. Recently, they've been putting a lot of focus on multi-layer PCB production, and they'd really like you guys to try their 6-layer boards. Thanks to large-scale manufacturing in China, their prices are very competitive. 5 100 by 100 6-layer boards are just $36.8. They also now offer Pad-on Via, an essential feature for high-density designs, at no additional cost. They're currently offering coupons for 6-layer boards, so now's a great time to try JLC PCB. Let's take a look at how much standby power there is. Here's the setup we used for the experiment. I wanted to evaluate the charger's performance accurately, so I used an AC power supply that outputs a clean sine wave with minimal distortion. The power meter and the USB charger are connected to the power supply to measure power consumption, which in this case is standby power. Now, let's actually give it a try. Powered on, and it's reading 100 volts. I'll connect the USB charger here. Here's what the power meter is showing. The current is very low, just around 0.3 milliamps. Let me adjust the current range. That should do it. At the top, you can see the active power. This shows how much standby power the USB charger is using. It's about 3 to 4 milliwatts. Below that, the reactive power is displayed. For a typical household, reactive power doesn't affect the electricity bill, so we won't be looking at it this time. Below that, the current is displayed. This shows how many amps are flowing from the outlet to the charger. The current flowing is very low, only about 0.3 milliamps. Simply plugging in the charger like this doesn't stabilize the power reading, so I decided to take a time average measurement of the power. The standby power of the Belkin charger, which is the main focus this time, is about 3.3 milliwatts. I also want to measure the standby power of other chargers as well, not only the Belkin charger, and compare the results. I'm going to test chargers I personally have from popular brands like Anker, CIO, Ugreen, and Apple. Standby power measurements are complete. Here are the results. All the chargers we measured today are shown in this graph, and the Belkin charger's standby power is impressively low at 3.38 milliwatts. Coming in second is Apple's 40-watt charger at 18.2 milliwatts, and then CIO's charger at 38.8 milliwatts. It seems that typical chargers consume around 40 to 50 milliwatts. I'm not sure if this is because of the way the manufacturers designed the chargers, or if it's something that applies to all USB chargers, but it appears that chargers with higher power ratings generally draw more standby power. Now, let's take a closer look at how much this low standby power actually affects your electricity costs. Here's the graph for annual electricity costs due to standby power. The calculation is based on Tokyo Electric Power's rates, using a rounded figure of 40 yen per kilowatt hour for simplicity. Belkin costs only 1.2 yen per year. Apple is next at 6.4 yen, and CIO comes in third at 13.6 yen. From this data, you can see that there is a difference of at least a few yen to several tens of yen. To be honest, the difference is so small that I don't really worry about choosing a charger based on its standby power. Taking everything into account, I'd say that the power conversion efficiency of a USB charger when it's actively being used is more important overall than its standby power. This diagram shows the USB charger's power conversion efficiency. It shows how efficiently the AC power supplied from the outlet is converted into DC power for USB charging during actual operation. The more efficiently a charger converts power, the less energy is lost during the power conversion, and as a result, the total power it draws from the wall outlet becomes lower. Let's do a quick calculation with two patterns to see how much the charger's efficiency really makes a difference. I calculated it for 90% and 91% efficiency. First, let's assume a USB charger with a conversion efficiency of 90%, operating at 30 watts, and used for 30 minutes per day over 365 days. Charging at 30 watts for 30 minutes is roughly enough to charge a smartphone to around 80%. At 90% conversion efficiency, the USB charger loses about 3.33 watts. This 333 watts is energy that does not contribute to charging and is instead lost during the conversion process. All things considered, the power lost during charging adds up to about 0.61 kilowatt hours per year. If the power conversion efficiency increases from 90% to 91% under the same conditions, the USB charger's power loss will be 2.97 watts. The energy lost during charging amounts to about 0.54 kilowatt hours per year. To get a better sense of the scale, let's compare these numbers with the data shown in this graph. This graph shows an estimate of the annual standby power consumption. Interestingly, the annual power loss during charging that I calculated earlier is actually about the same as the annual standby electricity consumption shown in this graph. In the previous calculation, increasing the efficiency from 90% to 91% reduced the electricity loss by only 0.07 kilowatt hours in total. As you can see, the impact of this small efficiency gain isn't really that significant. Increasing the efficiency of a USB charger in this price range from about 90% by even just 1% is actually pretty challenging. A 1% increase might seem small, but in reality, it means that the power loss has to be reduced by nearly 10%. By the way, in this estimation, I assume that charging takes place for 30 minutes each day at 30 watts. However, if you're using the charger to continuously supply tens of watts, standby power becomes almost negligible, and the focus shifts to power loss during charging and the charger's overall conversion efficiency. I also measured the efficiency of the Belkin charger. The vertical axis shows the charger's power conversion efficiency. The higher the value, the better the charger performs. The highest efficiency was 91.4% at a 20-volt output. For chargers in this price range, efficiency usually falls in the 91% to 92% range, so Belkin's performance is quite good. Lower standby power doesn't mean the charger performs worse, so you don't have to worry about it. I also measured the temperature of the charger. I used a thermal camera, and the maximum temperature was around 65 degrees Celsius. This level of temperature rise is pretty standard for a modern USB charger. I also tested whether thermal throttling occurs. Thermal throttling is a feature that intentionally reduces a USB charger's output power in order to prevent the device from overheating. This is the test setup. I continuously drew the maximum output power from the USB charger. Here are the test results. The horizontal axis shows elapsed time since the test started. The left vertical axis shows the charger's surface temperature, while the right vertical axis indicates its output power. The charger was outputting its maximum of 67 watts from the very beginning of the experiment, while its surface temperature steadily increased over time. Thermal throttling occurred 20 minutes after the experiment started. At that moment, the surface temperature was 58 degrees Celsius. After thermal throttling, the output power dropped to 50 watts. This mechanism keeps the charger's surface temperature from becoming too high, thereby protecting its internal circuits from potential damage. The temperature kept rising and stabilized at 68 degrees Celsius about 2 hours into the experiment. After wrapping up all of these experiments, I noticed while editing the video that I had overlooked an important aspect of the testing process. It would have been better to measure the standby power with the USB cable plugged in, rather than measuring it with the cable disconnected. Think about when you actually use the charger. Do you usually unplug the USB cable once charging is finished, or do you leave it connected? I would guess that many people simply leave it plugged in. Therefore, I will measure the standby power again with the USB cable plugged in. I'm now measuring the standby power consumption of this Belkin charger with no USB cable connected. Just like in the previous test, it's about 3 milliwatts. Let's go ahead and plug in the USB cable. Whoa, it's gone up. The standby power has increased to around 30 milliwatts, about 10 times higher than with no cable connected. I left it for about an hour, but the standby power hasn't really decreased. It's still sitting at about the same level. How should I put it? I feel like I've seen something I shouldn't have. By the way, this cable contains an e-marker chip. Some cables don't have one. So let's see what happens if we connect a cable without an e-marker. There's no increase in standby power. Interesting. So to summarize, with an e-marker equipped cable, the charger doesn't go into zero standby mode. But with a non-e-marker cable, it does go into zero standby mode. That's the result. So depending on which cable you connect, the standby power can rise to about the same level you'd see with other chargers. I tested a few other USB chargers with the e-marker cable as well. Here are the results. The Belkin charger had a standby power of 3.3 milliwatts, but when the USB cable was plugged in, the standby power increased to about 10 times, reaching 32.4 milliwatts. When the cable is plugged in, probably the internal circuit operates and exits the zero standby mode. For the other chargers that already consume some standby power, plugging in the USB cable didn't really make any noticeable difference to the standby power draw. I guess that's because the internal circuitry is active even without a cable connected. So if you want to fully take advantage of this charger's zero standby power, it's best to use a USB cable without an e-marker like this one, or simply unplug the cable after each time you charge a device. Next, let's take a look at the pros and cons of this charger's zero standby power mode. The main advantage is that the standby power is nearly zero. It's only about 3 milliwatts, so even if you leave it plugged in all year, it would only cost around 1 yen in electricity. The downside is that, depending on the cable you use, it can draw the same amount of standby power as other chargers. I think this is a pretty significant drawback. It kind of undermines the whole concept of the product. As for other downsides, I didn't notice anything in particular during my testing. However, looking at the Amazon reviews, some users report that, depending on the setup, the charger may unintentionally enter zero standby power mode and stop outputting power. So far, in my testing, the standby power draw per charger is pretty minimal. But once everyone in the family has one plugged in, that idle power starts to add up. If a zero standby mode like this were to become widely adopted as a standard feature, the effect at the individual level would still be quite small. But when applied at scale, the overall impact becomes significant. I really like the idea behind this product and the effort that has gone into reducing the standby power on this charger as much as possible. Now, let's take the charger apart and take a closer look at how it manages to reduce standby power. I removed part of the casing. This is the inside. This blue material is fairly soft and has a texture that feels similar to silicone. It's likely a thermally conductive compound used to provide thermal coupling between components. But it's not completely filled. You can see here the actual amount of material applied inside. On the backside of the USB port, there's a graphite sheet attached, which appears to be used for heat conduction. However, this graphite sheet is not tightly attached to the parts, as you can see. Since there's a visible gap here, it's unlikely that the sheet plays a significant role in thermal conduction. I'm not sure whether this was intentional or if it happened accidentally due to a manufacturing issue. I've taken off all the casing. We've got 1, 2, 3, 4 circuit boards. Let's take it apart even more. I've disassembled the circuit further. The circuit is basically a power supply using the flyback converter setup that's common in chargers. If you take a closer look, you'll see that a lot of them are semiconductors from Renesas, the Japanese company. This setup is pretty much the same as what's shown on Renesas website. Let's take a look at the main semiconductor components. First up, this MOSFET is a power semiconductor from Transform, which was acquired by Renesas in 2024. This MOSFET has an interesting internal structure. It combines a normally off low voltage silicon MOSFET with a normally on GaN HEMT in a cascode configuration, enabling it to function as a normally off transistor. Next to it is the IW9870 from Renesas, a flyback converter controller. From my research, it appears to be a product originally from Dialog Semiconductor, which Renesas acquired in 2021. Let's check out another board. Here's the IW610, a secondary side synchronous rectifier controller. And this one's from Renesas too. This is a buck boost controller from Intersil, which was acquired by Renesas in 2018. This charger has 2 USB-C outputs, and this component manages the delivery of different voltages to each port. Finally here, the USB PD controller, IW780. There are 2 of them. They are also Renesas products, but judging by the model numbers, they appear to have originally come from Dialog Semiconductor. I analyzed why the standby power of this USB charger is lower than that of other chargers. The low standby power is achieved by combining this flyback controller IC with the PD controller IC, which optimizes the charger's operation when no USB cable is connected. In this way, the charger is able to maintain an ultra-low standby power level. When no USB cable is connected, the PD controller senses this condition, and the flyback controller reduces the circuit's operation, putting it into a low power consumption mode. As a result, the circuit is nearly shut down, dramatically reducing power consumption. In this state, standby power drops to an extremely low level. Naturally, even in standby mode, the ICs continue to draw some power, so it's necessary that they are designed to minimize power usage as much as possible. Now that we understand how standby power is reduced, let's take a look at why it increases when a USB cable is connected. A closer look at the datasheet makes this clear. It specifies that when the flyback controller is combined with the PD controller, the charger's standby power drops to below 5 milliwatts whenever no USB cable is connected. In other words, even with this IC combination, plugging in a USB cable can cause the device to exit its zero standby power mode. The mystery has been solved. So I examined Belkin's zero standby power USB charger, tore it down, and analyzed it. When I measured the standby power, the result was 3 milliwatts. That's almost zero. However, I found that when an e-marker equipped cable is connected, standby power increases to nearly the same level as conventional USB chargers. Even so, the concept of minimizing standby power is eco-friendly and fascinating, and I hope we'll see more USB chargers like this going forward. I've put links in the description for the USB charger I used today, along with some other recommended chargers. Go ahead and check them out if you're interested. Thank you for watching. See you next time.